Welcome to Lesson 31, Electric Fields and Coulomb's Law. Throughout these next few lessons, I want you to notice the similarities between electric fields and gravitational fields. Here's the plan for today. The basics. Like charges repel, opposite charges attract. And the key mechanical fact, the thing that actually moves when something gets charged is the electron. Protons are locked in the nucleus, they don't go anywhere. So if an object has more electrons than positive charges, it's negatively charged. Remove electrons and it's left positive. Rub a balloon on your hair and you do exactly this. You put energy in and electrons are pulled from your hair onto the balloon. The balloon ends up negative and your hair ends up positive. And, being all positive, the hairs repel themselves and stand on end. Whether you can charge something this way depends on the material. In a conductor, the electrons are free. They slosh about and flee from a positive charge instantly, so charge redistributes itself immediately. In an insulator, however, the electrons are stuck in place, which means you can pluck them out individually. That's why you charge a balloon or a plastic rod, not a metal one. There's a nice demonstration called the shuttling ball experiment, where a charged ball bounces back and forth between two plates, ferrying charge across each time. Because it carries a known charge at a known rate, you get a measurable current out of it, which links charge directly back to current from lesson 17. And earthing. Connect something to the ground and any excess electrons flow away and equalise. Charge always settles at the lowest available potential, which is exactly the same instinct as water flowing downhill. There are 4 field patterns you need to be able to draw. 2 more than for gravitational, because we now have positive and negative charges. Before you draw any of them, however, fix your frame of reference. The arrows always show which way a positive test charge would move. Remember, test charge means a charge that is small enough so that it doesn't create a field that affects the one we're trying to measure. So, around a positive charge, the lines point radially outward. A positive test charge is pushed away. Around a negative charge, they point inward. Between 2 oppositely charged parallel plates, you get straight, evenly spaced parallel lines. A uniform field, just like gravity near the ground. Between 2 opposite charges, the lines curve out of the positive and into the negative. And for a point charge near a plate, the lines curve round and meet the plate at right angles. Now the law itself. How does the force depend on the charges? It grows with each of them, and with distance, inverse square. And it's the exact same reasoning as gravity. Draw the ring, the sphere, around the charge. The influence spreads out over the surface of the sphere, where area goes as r squared, so the force dilutes as 1 over r squared. That gives Coulomb's law. F equals 1 over 4 pi epsilon naught times q1 q2 over r squared. Or, bundling that constant up, just k q1 q2 over r squared. The constant comes from experiment, and the 4 pi is in there precisely because we're spreading over a sphere. But look at the shape of the equation. It's exactly the same form as Newton's law of gravitation. 2 sources multiplied together on top, r squared underneath, and a constant out the front. Swap masses for charges and big G for k, and you have the same law. One important difference is the sign convention, because now we have positive and negative, pushers and pullers. In Coulomb's law, a positive force means repulsion and a negative force means attraction. You just need to accept the convention. And this is precisely where the 2 laws part company. Gravity has no repulsion, so it never needs that sign. Electric forces do. The easy way to remember this is if Q1 is negative and Q2 is positive, the force will be attractive. But the negative gives the minus sign out the front, so we can remember that negative is attractive. That's the end of the video. Thanks for watching and check out my tutoring page below.